Let's try surjective. Right. So now surjective, remember the definition. It means every point, every element in your codomain is mapped to. Right? It's covered. So let's say you've got something like this. So you've got like 4 points here, you've got 3, and this point here is mapped to twice. Okay? That's okay in surjective. So that's, if it's surjective, yeah, F. But you've got a problem here. How do you, if you've got this point here, now it's mapped to twice. Right? There are 2 elements in A that map to it. So if you wanted to go back, it's not clear which way you go. Do you go back along that route to get to this point? Or do you go along from the same point? Or do you go that way to get to that point? But you're not allowed to do that, right? If G does that, it's not a function. Right? By definition, a function has to map to only one element in the codomain. So if you're going back, this would then be your domain, that would be your codomain. And you're not allowed to map from here to 2 different, it's not allowed. So it looks as though surjective is also out. So what does that leave? Well, the third possibility is bijective. So how about that? You're probably getting suspicious that that's what's going to be the case, right? Right, well, let's try bijective. So, now bijective is 1-to-1, remember? So, it's strictly 1-to-1. So if this is your set A, that's your set B, your F, if it's bijective, remember bijective by definition means injective and surjective, both, right? Both of those properties are needed. And if you think about it, bijective means 1-to-1. So you can go either way uniquely, right? So this little A here would map to B, and this little C here would map to D, and E to F, and so on, right? Now, if this function f is bijective, then G would map backwards uniquely, right? If f is bijective, then your G makes sense. You could if you start with B and you apply the function G to B, well, you just end up with A uniquely. And similarly with D, you'd end up with little c uniquely, and so on. So it looks as though you're getting suspicious that the condition you have to have on your f for a G, for this inverse function to exist, is that your f, the one you start with, is bijective. Okay, so that's what theorem 30 says. And it's quite a long theorem, so requires some patience. So I will state it here. So theorem 30 says it says f that maps A to B is bijective, bijective. Okay, call that statement P. You're probably sniffing that if and only if it's coming up, and that's true. Okay, so F is bijective. Mapping from A to B. It's bijective, so it'll look like that, 1-to-1. All right. Now if there is, that's like the reverse capital E, like mirror image. So if and only if there is a function G that maps B back to A, right, with the following properties. That G of F of A equals A. Right, so it cancels. So the G cancels out what the F does, and you just end up with what you started with, which is your little A. And that's true for all members of your set A, right? And F of G of B. Now G of B will take you back to A, so F of A will give you B. And that's true for all B belonging to set B. Now that's statement Q, right? That's theorem 30. Now it's an if and only if, so we have to prove it both ways. And proving that something's bijective, you have to prove that it's injective and surjective, right? So quite a few parts in this proof, so it'll take a while. That's why I suspect this lecture may go on for quite a while, with many parts. All right. So as usual, with an if and only if proof, you start with the if case. And so P if and only if Q. Right? P's the statement that your function f here is bijective, right? Is bijective. If and only if all this stuff. You know, that there is a function g that takes you back, and it has these properties. So if you do gf, you get what you started with. If you do fg, you get what you started with. Now, if you go from A to B, you'll start with letter A. If you go from big B back to big A, you'll start with a little letter B, right? So you end up with what you started with. Okay? And so effectively what you're saying is that this is what the theorem's saying. If f is bijective, then there is an inverse. Okay? Now it's an if and only if, so it goes both ways. Right? It's typical of if-ifs, IFF type proofs. So if f is bijective, there's an inverse. If there is an inverse, then f has to be bijective. Okay? Now we're suspicious, from this sort of intuitive kind of reasoning. There was something wrong if it was only injective or only surjective. It's got to be both. Okay? And if it is both, then you get this clean one-to-one, and then G maps back to A cleanly, and so on. All right. So that's the suspicion, and that's typical of pure maths research, right? You usually start with some kind of mathematical hunch, and that suggests maybe something like this as a theorem, and then you try to prove it. And if you do, right, you got a result. That's nice. And if it's a significant result, you can publish. And if it's really significant, like proving Fermat's last theorem, then you get famous. All right. So let's do the if case. So P if Q, P is true, if Q is true. So if Q is true, then P. Right? So the if case is you start with Q and you prove P. Now Q is this right hand side, the usual if case. So start with the right hand side and prove that it's bijective. Right? So we're given all this stuff. We're given these properties. Right? So we'll use those to try to prove that f is bijective. So try prove bijective. Okay, and that implies prove injective and surjective. Okay, so let's try to prove injective. How can we prove that F is injective? Well, from last lecture, how to prove that a function is injective is you you take two random elements, let's just call them A and B, from your codomain. You assume this is under F. So you assume that F of A equals F of B, right? And remember, these are just two random elements from your codomain. B, A, right? And you assume they're equal, and then prove that A equals B. Now, if that's true, then this mapping F is injective, right? If these two are equal, then these 2 points here have to be the same. Because you can't, if it's injective, you cannot have 2 points here mapped to the same point in B in your codomain. Right? That's, if you're a bit rusty on that, or you don't follow that, go back to the previous lecture and study proof that something is injective. Okay, so let's try to prove that. Okay, so we'll assume that F of A equals F of B. Right? This is the standard proof technique for showing that a function F is injective. And we're given this, right? We're going from Q to P. So this is true. We're assuming that's true. All right. Well, look, we've got properties like this and this. So we can do. So we've got GF of A is A and FG of B is B.